Well, good morning, and I'm just setting up everything to get going. All right, so there we go. We got the screen sharing on Discord, and I am already streaming to YouTube. So we are starting a little bit early today. In terms of the streaming, let's see. I can turn the webcam on just for the time being until we need that area back. All right, so the first thing we're going to do today is to take a look at the problem that I presented to you on Monday, which is summarized here. We'll talk about it in detail today to basically talk about how to analyze a problem like this and how to map it to the ways that we have been talking about how to count the number of outcomes and how to figure out the binomial distribution, because this is a problem that combines the two. So we need to know, when to use which technique. Um, so that's going to be one thing that we'll be talking about today. And then the other thing we'll be talking about today would be Dijkstra's algorithm. So Dijkstra's algorithm is in the graphs module. We talked about the algorithm just a little bit on the other day, so what we'll do today is to take a closer look, and we'll also go through a trace based on a specific example. So those are the two things that I want to accomplish today. I believe the 12th is our last day, so that would give us, approximately 2 weeks, to 4 classes or so. One class is going to be used up to talk about the final exam. So we have 3 classes left for new material. So we'll see how far we can go in terms of. I think we can finish graphs. It's only a question of do we have enough time to go through both time complexity and also predicate calculus. And if we don't have enough time, which one do we want to go over first? So I think time complexity is going to be more useful in general compared to predicate calculus. So that's going to be, we'll see, so we'll play by year until the end of the semester. And we got about 3 minutes to go. And this is the notes area, representing, what I'm going to be typing to explain the answer to the question that I posed the other day. All right. And the answer is not going to be, it's not simple, it's a little bit tedious, but the analysis part is actually not too bad. Basically, you just need to understand, how to look at each part of the problem, because there are 2 processes. So each process, one process is a counting problem, and then the other process is a binomial distribution problem. So we have to figure out which part is which part and how to look at the problem. So that's going to be one of the more important things that we need to kind of talk about today. And we got about 2 minutes before the class starts. We got 8 people on Discord and 1 person on YouTube. Okay, all right. So we got about 1/3 of the class here. So I don't know about you guys. In fall 2022, I am going back to be teaching 100% face-to-face back on campus. And it's going to be nice because I have my office. I have my brand spanking new office. I have new classrooms, new equipment. So it's going to be exciting for me, to get back on campus to teach. And for the first time, for the first time, I don't have to go outdoor to get to a classroom or the bathroom. where CMC used to be, to get to bathroom, I have to go to either the science complex, which is across this quote unquote street, or go to the cafeteria, which is also across the street. So when it rains, it's no fun. Now, it's all inside the same building. All the classrooms that I need to go to, they're all in the same building. So that's gonna be nice. And I got one of the offices with a view outside too. So, all right. Looking at the time, it is noon, so we're gonna get started now. All right. So this is the problem that I presented to you on the other day. So other than some kind of extra stuff, like the name of the person who's doing this. So this is the essence of the problem. We have two kinds of coins, and I'm just going to refer to these two kinds of coins as type A versus type B. So a type A coin is one that has a zero point 0.6 chance or 60% chance of landing on the head and 40% of a chance landing on the tail. And then a type B coin, on the other hand, has a 0.35 or 35% chance of landing on the head and 65% of a chance landing on the tail. A few open mics. All right, thank you. I didn't actually hear that. Anyway, so the thing is, so basically we have 9 coins altogether, right? Because we have 2 type A and 7 type Bs. So we have 9 coins altogether. And somebody is going to pick out 4 coins out of the 9 without replacement. So that means, we have some kind of a combination-ish kind of problem here, because we are taking 1 coin at a time out of the 9 coins without replacement. So once we have picked out the 4 coins, then we'll flip each one exactly once. And the question is asking, if we did that, okay, what are the chances that we end up with 2 coins with that land on the head and 2 coins that land on the tail? That's the question. So so one thing you can do, basically you can try to understand the problem is really just kind of go through the entire experiment in your head, okay? Or you can actually pull out some quarters if you want, and just kind of use a felt pen to write down A, okay, and then B, 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 B. So now you have your props ready, right? So you put all 9 coins into a coin purse, and then you just go shake it up, and then you draw 4 coins out of the purse, and then for each coin you just flip it and see what whether it's a head or a tail. So the question is, what are the chances that those 4 coins would end up with 2 head and 2 tail? All right. So having said that, okay, there are several really major branching that we need to consider. So the one branching that we need to consider is how do we make up those 4 coins, right? Because there are 3 ways to make up the 4 coins. That's the first thing that we need to understand. So I'm going to use a certain notation here. So it is possible that you have just 4 type Bs, right? Because there are 7 type B coins, so it's entirely possible that you just picked out 4 type B coins and that's it. On the other hand, it is also possible to pick out 1 of the type A coins and then 3 of the type B coins from the first process as you're taking coins out of the coin purse. Or you can also pick out both of the type A coins and 2 of the type B coins. So this is the first level of breaking up the problem, is to basically look at, okay, so how can I make up the 4 coins that I'm going to flip out of the 2 types that are kind of mixed up in the purse? So are we good so far? Are there any questions about this part? Okay, all good, excellent. All right, so the next thing we want to do, which I should probably explain up here. Okay, so I'm going to put another point here. Is how we look at the coins. Okay, because it's this. we have to look at each coin as a unique coin, even though two of the coins belong to the same type, and then the other seven coins belong to another type. In other words, you might want to look at your coins and label your coins not only as A versus B, but we have A1, A2 as the two type A coins, and then you have B1, B2, B3, all the way up to B7 as the type B coins. Okay, now this is really important because when we need to figure out, how many ways can we pick out for type B coins, now we have to consider the option of, okay, so we can type, we can pick out B1, B2, B3, B4, and then that's it, right? So this is one way to pick out, four type B coins. I'll give you another example. Obviously, this is going to be a little bit too much, to enumerate every single one. So this is another way to type out, to pick out four type B coins, and this is going to be. I'm just going to make some random changes here. Okay, obviously this is not that systematic, so this is yet another way. So the question is, how many ways do we have to pick out four type B coins? That's the question. And 35 is okay. So the question is more about how do we formulate this, right? How do we formulate this? So this means, out of the seven type B coins, how many ways do we have to pick out four of them? Okay, there we go. So that is the question. So if I formulate the question like this, obviously this is without replacement. So it's going to be 7 choose 4. That is correct. So then Danny is correct, and so is Elijah. So it's not just 35, but how do we get to 35? So that the answer is, let me put it in equation mode. It is 7 choose 4. And is that 35? I'm not 100% sure. Let me double check because I'm not 100% sure that is supposed to be 35. So I'm just going to do a combin of 7, 4. And it is 35. Very good. Okay, so I just want to double check. Not that I don't trust you guys, okay? Yeah. I just wanted to make sure. Okay, so we'll go ahead and say this is exactly 35. All right. So now we are not quite done here yet. However, we can we can work out the number of ways to pick out one type A and three type Bs. Okay, so once again, using examples is really important to help you kind of understand what this is all about. So A1, B1, B2, B3 is one way to only have one type A coin and three type B coins. Another way is to have A2 and then B3, B5, B7, yeah, whoops, there we go, and so on. So now the question is, how many ways can we do this? Now, this one looks a little bit more complex because, it's not just that out of the 7 coins we need 3 of the type Bs. We also have to figure out, the type A. So I'm going to break it up into 2 subparts. Okay, so we'll break it up into two subparts here. One is how many ways to pick out 3 of the 7 type B coins, and I think all of you should know, the answer to that one now, right? Because it's just like, oh, okay, since we already know how to compute, how many ways we can choose 4 out of 7. This one is okay, super easy because it is just 7 choose 3. Okay, because it's kind of using the same method here. And then we'll repeat the question. So this time it is picking 1 out of the 2 type A coins. So in that case, you can see how I just I used the most lazy approach. I copy and paste the entire line and just change a few things so that it fits what we are trying to do. So it is not difficult to understand how I just changed the 7 choose 3 to 2 choose 1. Are we good so far in terms of individually treating the type B coins as one subproblem and treating the type A coins as a subproblem? Are we good so far with that? And I need to make sure that I can read the text channel. There we go. All right. I'm not seeing any questions, so I am going to guess this part is okay. So now the question is, how do we combine these two numbers, right? Are we adding these two numbers because, of the 4 coins, there are 3 of them being type B and only 1 of them being type A? Or are we going to multiply these two numbers? And if we, what is the rationale behind which operator we should be using? That's the question. Okay, it's not just that oh, we know it is supposed to be a multiplication, or we know it is supposed to be an addition. The question is, why is it a multiplication? Why do we choose that operator? All right, so I'm gonna let you guys to try to answer that question in the text channel, and if nobody is answering it, then I'll go ahead and answer it. All right, it's multiplied because we have they're actually not dependent events, they are independent events. That's actually why we are multiplying. So let me just give you it's not exactly a tree, but it may give you the idea. Okay, so if we use a tree view, we can say, okay, what if we choose the A1 here? So if we choose the A1, then we can say, okay, in terms of the B's, we can choose B1, B2, B3, or we can choose B1, B2, B4, blah blah blah, right? And then when we choose A2 as the type A coin, then we have the same thing, right? B1, B2, B3. Okay, I'm too lazy to retype everything, so I'm just copying and pasting here. So you can see how this part here is going to be the same, because we have 7 choose 3 of these things, and we also have 7 choose 3 of these things, but each subpart here is paired with a different type A coin. This part here is paired with a type with A1 as a coin. This one here is paired with A2 as a type A coin. So when we look at the total number of these individual possibilities, we are basically saying, oh, so if we know how many of these cases we have, which is 7 choose 3, we just have to multiply that by the ways that we can choose the type A coins. And that's why it is multiplied, because when you are looking at this from the tree perspective, the subtree under A1 and the subtree under A2 are indeed the same. So when we are counting the number of branches, it's just a multiplication. Okay, so what is the there's a term for that. What is the fan out ratio of the type A, and what is the fan out ratio of the type B? Multiply those two fan out ratios, and you have your total number. All right. Okay, I'm just reading the text channel. So this calculation would not count A1, B1, B2, B3 as different from B1, A1, B2, B3. That is correct, because we are not, it's not order dependent. Okay, because all we need to know is how many A's do we have and how many B's do we have. The ordering of those coins is not important. So it is 2x, but it's not just that it is 2x. It is how we combine the 2 choose 1 and the 7 choose 3. So I'm going to give you a quick summary here. Okay, so we'll just kind of go back to this level of indentation. So we have, there are, first of all, we have 7. Oh, let's do A first, right? 2 choose 1. Choose 1 times C dot 7 choose 3 ways to pick out 1 type A and 3 type B coins. There we go. And I'm just going to fix up some hyphenation here. All right, there we go. And that number turns out to be 70 because 2 choose 1 is 2, and then 7 choose 3 is the same as 7 choose 4, which is 35. So when people look at this and go like, oh, so 4B is a special case because there are no type A coins. So let me kind of go back and fix that one, because I don't want you guys to think about this as that's actually a special case, because it is nothing special. Because what I did not say is when you have all 4 coins coming from type B, you have 0 coin coming from type A. So the question is, would this still work out using the same general equation? And the answer is yes, it will still work out using the general equation. And I just have to go back and change that a little bit here. So now we have to add one more sentence here. So out of the 2 type A coins, how many ways do we have to pick out none of them? So the answer is we have a 2 choose 0. And what do you think is the answer of 2 choose 0? In other words, this is the number that I should update now. Instead of 35, what should it be? What is 2 choose 0? And Chris is correct. It is 1 indeed. All right. So that means so the total number, okay, so the total number here, so let me just kind of add one more sentence here. So the number of ways to pick out 0 of type A, oops, typo, type A, and 4 of type B, type B coins is, okay, so this part is not a surprise, but I really like to generalize what we had earlier, because this time we have 0 choose 0, excuse me, 2 choose 0 times 7, oops, 7 choose 4. All right, so now this is nice in a way, because now when you look at this setup, is really very similar, or there's a structural similarity between that and what we have down here, because now you can see the top numbers are basically based on how many type A do we have, how many type B's do we have, and then the bottom number is they have to add up to 4. So if we start with a 0 on this side, then it has to be a 4 on the other side. If we start with a 1 on this side, it has to be a 3 on the other side. So are you guys seeing how I'm trying to generalize the approach? Because once you have a generalized pattern, then the next one is going to be like super easy, because it's just like, oh, okay. So without any further explanation, 2A to B is just going to be like this, right? The number of ways is, all right, so we're just going to use the same format, because I'm hoping you guys can see the pattern already. So it's 2 choose 2 because we have both of the type A's in this case, and that has to be multiplied by 7 choose 2 in this case, because out of the 7, this time we only need to choose 2 of those, and that number turns out to be, okay, I need to go back to my spreadsheet here. So it's combin 7 2, and that's 21. All right, there we go. 2 choose 2 is 1. Okay, so this part here, the left hand side is 1. 7 choose 2 is 21, because it is 7 times 6, the whole thing divided by 2. So 7 times 6 is 42. 42 divided by 2 factorial, which is just 2, is 21. So 21 does make sense here. So I'm going to pause and make sure that we are all comfortable with the numbers that we are looking at here, the number of branches for each way to choose, to pick out 4 coins. So this turns out to be 35, because 2 choose 0 is a 1. And then the second way is 70, and then the third way is 21. So we have 35, we have 70, and then we have 21. Are we good so far? Let me switch back to the text channel because I can't hear the notification for some strange reason. All right, so Marco is typing, so we are good here. All right, Chandra says it's okay. All right, that is always true. You are correct. So, okay, that's a very good observation, Marco, because if you think about, we have 9 things total, right? We just have to pick 4 things out of the 9. So that means these should all add up to 9 choose 4. And 9 choose 4 turned out to be exactly the same as the sum of 35, 70, and 21, which is 126. Thank you. So it does make sense. Okay, very good. Okay, so now what do we do, right? So now we look at each subcase. So we're going to go back to 0A4B, and then we'll take a look at what do we do in that case. So we go back to this one. Well, actually, I just lied, because that's a very extreme case because we have 0A. So we're going to take a look at 1A3B first, okay? Because that is a more general case. We have 1 of one type and then 3 of the other type, so it's not just all of one type. So now the next question here is to ask, okay, so let me point out the cursor here. So right now we're trying to ask the question. So now that we know of the 4 coins, we have 1 type A and 3 type Bs, and then we flip each one, right? What are the chances that we end up with 2 heads and 2 tails? So the analysis of this, okay, so we have to now say, okay, how can we end up with 2 head, 2 tails? So that's not it's not as simple as most people think it is, because it is possible that it is your A type that is the head that contributes 1 head, and then the other head has to be contributed by the Bs, one of the Bs, or it is possible that both heads are contributed by the Bs, and then the type A is contributing a tail. Okay, so I'm just going to use a different notation here to basically say, there's 1 type A, landing on the head, 1 type B and landing on the head, and then 2 type B's landing on the tail. That's one way to end up with 2 heads and 2 tails out of these 4 coins, knowing that 1 of them is a type A and 3 of them are type B's. So the other way is exactly the opposite. We have 2 type B's contributing both of the coins landing on the head, 1 type A landing on the tail, and then the remaining type B is also landing on the tail. So the way I'm going to write this is going to be, I'll reorder this a little bit for a reason, but that reason will be obvious later on. So are we doing okay so far, to come up with these 2 sub cases, even though we already know that, out of the 4 coins, 1 is a type A and 3 are type B's. So we end up with these 2 sub cases of, how we can end up with 2 heads and 2 tails. Are we good so far? All right, cool. All right, so now we look at this and go like, okay, how do we calculate, this probability? So at this point, it is a binomial distribution. Now, how do we know it's a binomial distribution? Because for each subproblem here, it is now just flipping a coin, which means there are always 2 outcomes, which means it is with replacement. And because there are only 2 possible outcomes per trial, it is a binomial distribution. So with a binomial distribution, so we'll say, for the type A, we use the binomial distribution, the binomial theorem to figure out, okay, so what are we going to do here? For the type A, the probability is going to be, so for each term in a binomial distribution, it's going to look like this, okay? It's going to look like, I'll give you a template first, and then we'll go back and fill in the template. It's going to be some x, choose some y, and then we'll have, okay, now we need to have, I'm going to use AH as the probability, or A subscript H as the probability of a type A coin landing on the head. And that's going to be to the power of something. So we'll say v here. And then just as a general form, there's always a multiplication by a type A landing on the tail to the power of some W here. All right. Well, that doesn't look very good, does it? Why are we treating the coins in unique when there are only two different types? So we treat the coins individually because that's how we can figure out how many ways we can end up with 1A and 3Bs or 2As and 2Bs, because otherwise there's no way to figure that out. It's just okay. So let's go back to the lotto problem, right? So in a lotto drawing, okay, and once they pick out the five numbers, the five winning numbers, so obviously those five numbers are different, but they are all quote unquote winning numbers. So in this case, we have two different types of coins. So all the type A coins share some common attributes, which is the chances of landing on the head versus the chances of landing on the tail, and all the type B coins would also share the same characteristics. But each coin is still different. It's still unique from the perspective of when you pick a coin out of the purse, each coin should be considered different from the other coins from that perspective. So when you map this problem back to the lotto problem, if I want to get the $10 prize, from my lotto ticket, I will need three of the numbers on my lotto ticket to match the winning numbers, and then two of those remaining numbers not to match the winning numbers. So in that case, the total number of tickets that can get me to win the $10 prize is going to be 5 choose 3, because there are 5 winning numbers. I need to choose 3 of those on my ticket. So it's 5 choose 3. But at the same time, don't forget that there are 2 other numbers that we need on the lotto ticket. So those 2 numbers have to be chosen from the non-winning numbers. There are 69 numbers to choose from, 5 of which are the winning numbers. So that means there are 64 non-winning numbers. So we need 64 choose 2 to account for the non-winning numbers on my ticket. So that is why we have to multiply 5 choose 3 and 64 choose 2. That product is going to tell us how many unique tickets will basically earn you the $10 prize. So is that helping? Because I'm trying to draw a parallel between the lotto problem and the problem that we're trying to solve here. The 69 comes from the rule of the game. So they choose numbers from 1 to 69 for the winning numbers, for the first 5 winning numbers. The Powerball number is from 1 to 26, and it has absolutely nothing to do with what is already chosen as the winning numbers. So that's just part of the rule of the game. So the 69 is really just part of the rules of the game. And it just so happened that 69 factorial is the last factorial that my Casio calculator can compute. That part is just completely coincidental. I'm sure it's just coincidental. Not. All right, so getting back to the problem that we have on hand here. So we know the probability is going to have this particular format. So now the question is, what should go where, right? So now we have to go back to the question. What is the probability of a type A landing on the head again? .6. Okay, thank you. So this one is 0.6, and this one is going to be a 0.4, because it has to be 1 minus the 0.6. So now the question is, what about the x choose y? Okay, what should be x and what should be y? So as it turns out, in this case, both are 1s. Well, it depends on how whether you want to count the heads or whether you want to count the tails. But assuming that we are counting the heads, so out of one coin, we want it to land on the head. That's why it's 1-1, and the power that we want to raise 0.62 would match the number of heads that we want, which is a 1. So that means W is going to be 1 minus 1, because out of one toss, we already want that one toss to be landing on the head. So what is the number of tails do we want? It's going to be 0. So that is how we come up with the numbers, corresponding to this particular template. All right, so now, and obviously someone is going to say, but Tech, this is like absurdly more complicated than it needs to be, because everybody knows your point for anything raised to the power of 0 is just 1. Why do you want to, keep on saying, multiply, by 4 to the power of 0? That's because I want a general pattern that can be easily reapplied to a different case, like the type B's, right? So now we want to deal with the type B's. So with the type B's, we have 3 of them, of which we want 2 to be landing on the head. So the ones that are landing on the head, I think the probability is 0.35, and it's asked to be raised to the power of 2, which is the number of heads that we want. And then the one that is landing on the tail would end up with a chance of 0.65, which is 1 minus 0.35, and it has to be raised to the power of 3 minus 2, which is 1. So now, this is why I want the general pattern, because now I can just reapply the pattern over and over again. So, are we doing okay so far? Why we end up with these two numbers? Why we end up with a 1 choose 1 times 6 to the power of 1 times 4 to the power of 0, and why we end up with a 3 choose 2 times 0.35 to the power of 2 times 0.65 to the power of 1. This part is completely based on binomial distribution, and we use one for the type A's, and then we use the other one for the type B's. Why is it 3 choose 2? Because, well, guess what? We have oh, okay, okay, you're right. Okay, I did not read my assumption correctly, because the assumption here says we only want one of the 3 type B's to land on the head. I forgot about that entirely, so I apologize that I kind of messed up there. There we go. Now it makes more sense, right? Because now it's consistent with we want one of the type B's to land on the head, and then the remaining of the type B's to land on the tail. So of the 3, we only want to choose 1, because that's the one that we want to land on the head, and it has a chance of 0.35 to the power of 1. And then of the other 2, we want them to land on the tail, which is 0.65, but it has to raise to the power of the number of coins that we want to land on tail, which is 2. So thank you, Danny. That is a very good correction there, because otherwise I would have moved on with the wrong assumption about this question. Very good. All right. Oh, no. I just made a mistake. All right. So now, once again, we have 2 numbers. Are we adding these 2 numbers, or are we multiplying these 2 numbers? Because there's always that question, right? We got 2 numbers. We know somehow they are related. They're part of the solution of the same thing. But how do we combine them? Are we adding, or are we multiplying these? We are multiplying. Yep. So we have to multiply, because so one way you can think about this is, out of the 4 coins, okay, maybe at one point in time you just go like, oh, okay, I'm gonna label which one is a type A and which one is a type B. So now out of the 4 coins that you have chosen, this is the one that is the type A, and these 3 are the ones that are the type B's, right? So once you know the types of the coins, then you use a tree again to look at all the probabilities. Okay, so let me illustrate using a tree here. So I'll try my best to use a markdown to represent a tree. I know you guys are thinking, mermaid, you can use mermaid. Yes, I could, but I can also use a slightly different representation here. So here's the tree representation. So the tree representation is to say of the type A, we want it to land on the head, or we can have the type A landing on the tail. Now with the type A, landing on the head, and this is the only one. This is the only one A. We want the type B, okay, we want one type B to land on the head also. We want another type B to land on the tail, another type B to land on the tail, or we want the type B, one of the type Bs to land on the head, another one to land on the head, another one to land on the tail. And the same thing for AT, right? Because I'm just going to do the lazy thing and copy and paste here. All right. So when you have a tree representation like this, the probability of the A type landing on the head and the probability of one of the type B landing on the head and two of the type B's landing on the tail, by the time you get to the end of the entire experiment, you have to go through every single one of these, and that's why the probabilities are multiplied and not added, because you have your chances of having the type A to land on the head, but you need the type A to land on the head first, and then you have the type B to land on the head, and then you have two type B's to land on the tail. So that's why it is multiplied, because these events here, they occur after this particular event over here, or I should say trial. So this trial happens first, or this is the outcome of one trial, this is the outcome of the other three trials, and these trials are done sequentially. So when you go all the way to the end, then you have to multiply the probabilities, because this is representing the overall probability of both of these cases. But for each case, it is basically they have to share the same probability of just the type A landing on the head, and that's why they have to be multiplied. I'm not sure whether that explanation is good enough for you guys or not, but that's the way that I look at it. Is but by the time you get to just AH, that's the probability of just the type A coin landing on the head, regardless of how the type B's are doing. So if you want to look at the type B's, also when you want to consider the type B's, then they are basically sharing the probability of the type A landing on the head in this case. And in this case, the type B, what the type B's are doing depends on the probability of the type A landing on the tail. So that dependency is why we are multiplying. The trials are independent, however, because they are in a sequence, so the probability is not independent. They are, they basically form a long chain where the probabilities are multiplied. Is that making any sense to you guys? Because if not, I can try to explain it in a different way. We are looking at 2H2. You're correct. Okay, so that's a very good point, because if we need to count all of them, there's also BH, 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 and there's also the case of a BT, BT, BT. So out of these four, we don't care about this one, because that's not what we want to count. This one is do care, this one is don't care, and this one is don't care also. So these four, if ignoring the probability of the AH, these three should add up to be 1, because that accounts for all the possible cases of when you have only 3 type B coins, you're gonna have all heads, all tails, two head, one tail, and one tail, two heads. So so the probability of all of these should add up to 1. But since this is the only one that we care about, so we need to multiply just the probability of this to the AH. So the other one is kind of the same thing. Okay, so we'll take a look at the 4 things and point out which one we care about in that case. All right, so out of this, we want one more BT and then 2 heads from B. So that would be this one. So with this one, we do care. And then the other ones, we don't care. That's very good, Marco. You just pointed out, one thing that I did not explain in the whole thing. Which one do we care? But in terms of adding up the probabilities of these 4 options should add up to 1, and then the probability of these 4 should also add up to 1. I shouldn't say options; these are experiment outcomes. So are we good so far to why we are multiplying and not adding? All right. So, all right, cool. All right. So now we have this one. And so after looking at everything, we can now go back to, I'm just looking at the indentation level. We can do one over here. So now we have these 2 numbers multiplied. So I'll just kind of copy that down here. All right, so let me see what is the best way to copy and paste it here, because I just need to all right, so here's one, and here's the other one. And then we just remove the 2 dollar signs and then give it another C dot. Alright, so it's still not liking it. So I'm messing up the format somewhere. Let's see. There we go. Alright. So now we know the probability of out of the 4 coins, we have chosen 1 type A and 3 type B coins. So if under that particular case, if we want to figure out the probability of the type A coin landing on the head, one of the type B's also landing on the head, but the other 2 type B's landing on the tail, this is that probability, and it has to be multiplied by 70, which is 2 choose 1 times 7 choose 3, to become the contributor of only this portion. So you might look at this and go like, oh man, that's going to be complicated, because what about the other case? What about this one over here? How are we going to factor the, oh, not here, but here. So how are we going to factor out the probability of both of the 2 of the type B's landing on the head, 1 of the type B's landing on the tail, and 1 of the type A, the only type A landing on the tail? So how will we compute that? So what I'll do is I'm going to copy and paste the equation here, and we'll go ahead and choose how to change this, right? So how are we going to change this? Is it's going to be 1 choose 0, because we do not want the type A to land on the head. We want it to land on the tail. So the probability of landing on the head should raise to the power of 0, but then the probability of landing on the tail should be raised to the power of 1. Of the 3 type B coins, we want 2 of them to land on the head, so the power or the exponent of the probability of landing on the head should be 2, and then the exponent of the probability landing on the tail for the type B should now be a 3 minus 2, which is a 1. All right. Exactly. So Nathan is correct. We just want one of the point 0.4, and this is a very long way of saying just point 0.4. But I'm maintaining the format, okay? I'm maintaining the format because this is the format that we are going to use for the other two cases. Because once we figure out the format, once we understand the pattern, we are now just reapplying the pattern to solve the other two cases, even though they seem a little bit more extreme. Okay, so now we are going to first denote what we want. So in this case, we have two A's and two B's. So once we have two A's and two B's, then we can say we have one way to do this, which is 2BH, 2AT, which means both of the heads are coming from the type B coins, and two of the tails, both of the tails are coming from the type A coins. So we have several subcases like this. This is one of them. So now we just have to change the equations. And I probably want to fix the order like this. 2BH, there we go. So out of the two type A coins, okay, dismiss. I have a meeting starting at 1 o'clock. I'm not gonna make it, so my reminder just kind of pops up and warn me about that. Okay, so out of the two type A coins, we want both of them to be tails. So the raising 6.6 to the power of 0 is still correct, but the 0.4 should be raised to the power of 2. Now, based on the so out of the two type B coins, we want both of them to land on the head. So 2 choose 2, landing on the head, and the probability of landing on the tail should now get a 0. All right, can we express this as PA plus QA times bar A bar, which is the number of A's, PB plus QB times raised to the power of B. No, it's not just that, because if you did just that, you would not be using the combination. In other words, this 3 choose 1 and this 3 choose 2 is not factored in what Luke is suggesting. Now there's a format, right? You can probably tell that there's a format to all of this. Okay, so we'll handle the other one. So now we have the other way is to have two type A's landing on the head, both of the type B's landing on the tail. So that's just the flip version of what we had. So we have 2 choose 2 because we are counting the number of heads that we want. And then the exponent of the probability of landing on the head is now 2. The exponent of landing on the tail is going to be 0. And then on the other side of the type B's, we do not want anything landing on the head. So we have 2 choose 0. And then 0.35 is raised to the power of 0 because we do not want any thing to land on the head. And then the ones that are landing on the tail, we have 2 of those. So now there is that. And then we have one more configuration, right? Because in the other configuration, we have basically one AH, one AT, and one BH, and one BT. So that's the third way of ending up with 2 heads and 2 tails, which is one of the 2 type A's lands on the head, one of the 2 type B's also land on the head, and then the remaining type A is landing on the tail, and then the remaining type B is also landing on the tail. But since we have this general format, it's super easy to do this, right? Because now we just say, oh, out of the 2 type A's, we want 1 to land on the head. So the exponent corresponding to the probability of landing on the head is 1, and the exponent of the probability of landing on the tail is also 1. And the same thing over on the other side. There's a 1 here, and also a 1 over here. Alright, so I'm just going to pause a little bit and see if there are any questions at this point. Alright. I'm not seeing any questions. That can be because some people are just completely lost. Um, all right, so Nathan is typing something. I'm going to kind of work out for the first case, which appears to be a special case because there are no type A's in that case. But that's not how I want to see it. Okay, the way I want to see it is just we are reapplying the same um, equation as what we have down there. So we'll have this thing here, and I'm looking at the indentation level. Okay, so there we go. So this one is, we have none of the A's, so none of the A's can really contribute anything. So we have 0AH, 0AT, and everything is a type B, right? So both of the heads, they have to be contributed by the type B's, and both of the tails also needs to be contributed by the type B's. So now we look at that, and then we look at the general equation here, or the general expression, and then we just go back here and reapply that. I am going through this and find out where I'm supposed to put it. I might have put it in the wrong place. Yeah, I might have put it in the wrong place. Yep. Okay, so I got it. I put it at the wrong place, so I'm gonna take both of these out and put it where they're supposed to be, which is under that. So we're gonna put it here. There we go. Now they're at the right place. All right. So getting back to what you guys can see, which is here. So now we are looking at the case where we have the 4 coins that are chosen. None of them is a type A, so all 4 are type B's. So the only way we can have two heads and 2 tails is both of the heads are contributed by type B's, both of the tails are also contributed by type B's. So now when we look at the equation, we have none of the type A's, right? So of the none of the type A's, we're going to have none of those being heads. So this is a 0 here, and is that one. So this part is still here. Even though we have no type A coins now whatsoever, I'm just going to look at this and go like, okay, cool. This is not a special case. So I just say that out of 0 type A's, we want 0 of them to land on the head and 0 of them to land on the tail. I know it sounds weird, but this is, I think, is the best way to look at it, because this way we're reapplying the same format, the same general format of the expression, and we're just changing up the numbers a little bit, because this time we have 4 of the type B's, of which we want 2 of them to land on the head. So the probability associated with landing on the head is raised to the power of 2, and then the remaining portion of that also has to be raised to the power of 2, because those are the 2 tails contributed by the type B's. Choosing nothing from nothing. There's one way to do it. That's the point, okay? Elijah, there's one way to choose nothing out of nothing. It still makes sense. And that's why, and this is, I think this is really important, okay? Because it's not just important because, okay, TAC, you're working with a very specific problem here, and that's why it's important. No, generally speaking, the more you can come up with a general pattern that can describe more things, the better, okay? Because that's what programming is all about, right? Because programming is figuring out the pattern of steps that you need to perform in order to solve a problem. So you don't want to have a lot of special cases and go like, if it is like this, this is how we do it. If it's like this, we're going to do it that way. That is less desirable than an approach that is much more generalized. It's like, okay, doesn't matter whether it's this special case or this special case here. I have a way to unify everything into one single problem description, and as a result, they have one algorithm to solve the problem. So generally speaking, this is the approach that I prefer to do things, which is to look at the overall pattern that can describe as many things as possible, and not to kind of shuffle things into, oh, this is a special bin just for this, this is another special bin just for that. Um, but that's just that's philosophy. Okay, that's not exactly related to this problem here. All right. Okay, so now what do we do, right? So this one is easy, because what we do is we just have to multiply the 35 by this probability here, and then we have the chances of, picking exactly for type B out of the 9 coins total, and ending up with 2 heads and 2 tails. Okay, so when you multiply this 35 by this binomial product, binomial expression product, then we have the chances of picking 4 type B's out of the 9 coins and somehow end up with 2 heads and 2 tails. And what about the 1A, 3B? Okay, the 1A, 3B looks kind of complicated because there are a lot of subcases. So what are we going to do with all the subcases? Okay, the first thing is, how many ways can we end up with one type A and 3 type B's? So we just figured that out, right? Figure out there are 70 ways to do this. So each of these 70 ways ends up with 1 type A and 3 type B's. So why are there 70 ways to do this? Well, that's because we have 2 type A coins. We label them as 1A, A1 and A2, and there are 7 type B coins. We label those as B1 to B7. So these are all considered distinct combinations, even though they end up with the same characteristic of one of the coins has a 0.6 chance of landing on the head, and the other 3 has a 0.35 chance landing on the head. So that's why we end up with a 70 here. So, but when you look at each one of the 70 ways, then we say, okay, so if you want to look at, how we end up with 1A, 1AH, 1BH, and 2 BTs, then we end up with this probability down here. Okay, if you want to look at how, what about 2BH, 1BT, and 1AT, then we have this probability here. So now we know these 3 numbers are related. The 70, this thing here, and this thing here, they're all related. So the question is, how do we combine them into one single probability? So what do you guys think? Add and then multiply, right? So we add up these 2 numbers, and then the sum of these 2 numbers will be multiplied by the 70 here. And then that final product is going to represent the probability of choosing 1 type A, 3 type B's out of the 9 coins, and then somehow end up with 2 heads and 2 tails. Are we doing okay so far with that? So we add up these 2 numbers, and then the sum of these 2 numbers will be multiplied by the 70, and then that number in the end is going to tell us the probability of choosing 1 type A, 3 type B's, and ending up with 2 heads and 2 tails. So the last one, it's going to be easy too, because we just end up with one more number to add. So the summation is going to sum up these 3 numbers. That sum is going to be multiplied by the 21. So now we end up with the chances of picking 2 type A's, 2 type B's from the 9 coins that we have, and ending up with 2 heads and 2 tails. Whew, okay, so any questions? So now we have 3 numbers, and then we just add up those 3 numbers, and that would be the total probability of choosing 4 coins out of 9 and ending up with 2 heads and 2 tails. Actually, I take it back. I take it back because you have to divide it by omega. You have to divide it by the cardinality of omega, which is the total number of ways of choosing 4 things out of 9. So I forgot about that. So you have to divide the numbers that I just mentioned, sum them up, and then divide the whole thing by 9 choose 4. All right. So I think most of you are now thinking, so what is the solution? What is the actual number as an answer? I got it in computed. So let me just kind of give you the actual answer here. Oh, all right. So let me be careful. Okay, final answer is 0.3522 blah blah blah. Okay, so it's about there. Does that make sense to you that it's close to 0.35? I mean, why is it not close to 0.6 and rather it is close to 0.35? Exactly, because there are only 2 of the type A coins and there are 7 of the type B coins. So just intuitively speaking, we are leaning a lot more to the type B behavior. But to find out the exact number, this is the kind of analysis that you have to go through. So the bottom line here is, are we understanding, how we figure out all the different components? I mean, once we figure out the general pattern, it's easy, right? So the question is, how do we figure out the general pattern? There are 2 processes, okay? The first process or the first experiment has to do with choosing 4 coins out of the 9 coins. But we have to classify, those, counts into 3 categories. The 3 categories would be 2 type A, 2 type Bs, 1 type A, 3 type Bs, and 4 type A and 4 excuse me 0 type A and 4 type Bs. So we have to separate into these 3 general categories. For each category, okay, this is not this is an easy one to figure out because we got 0 of the A's. So we're going to choose the one that is kind of intermediate. So when we have 1 A and 3 B's, now you have to figure out how can we distribute the heads and the tail between the type A's and the type B's. So with 1A and 3Bs, we can have, okay, so let's just say that 1A is contributing a head. That means the other head has to come from one of the Bs, and then both of the tails have to come from the Bs, versus we have 2 of the heads coming from the Bs and 1 of the tail coming from the Bs, and then the A also has to contribute the tail. So that would be the secondary consideration is, how do we figure out some of those subcases. So those subcases is summarized here and also here, and then for each one of those subcases it has 2 binomial distribution terms, one to deal with all the type B's and then the other one to deal with all the type A's. So this is the part that deals with all the type A's, and this is the part that deals with all the type B's. So once we figure out, the general pattern, we just reapply that general pattern depending on, how many type A's, how many type B's, how many of the type A's are landing on the head, how many of the type B's are landing on the head, and came up with, these, different variations. So, yep, exactly. So Danny said, so you add them up, multiply by the number of ways to get a combo, and then also divide by 9, choose 4. Right. So so once again, what we are adding are these 3 numbers. So let me see if I can just kind of highlight. So these 3 numbers, you add them up, it becomes a sum. That sum is multiplied by 21 in this case. So you then you put it aside. You add up these 2 numbers, and then you multiply those 2 by 70 in this case. And then last, you figure out this number, and then you multiply that number by 35. Where's my 35? There we go. So we multiply that number by 35. So now you have three numbers, and then those three numbers are also going to be added. So you have one general sum, one overall sum in the end. That sum is going to exceed 1 for sure. Okay, so you have to divide that by 9 choose 4, because 9 choose 4 is the cardinality of omega. That's the total number of ways to choose 4 things out of 9. Is that okay? So there are a few things that are really important that you guys kind of need to kind of let it sink in, kind of do some processing and write it in your own words. Okay. The first one is, how do we separate the experiments? So you basically want to go through this in your head and go like, okay, the first thing we need to do is to choose 4 coins out of 9. But we have these different categories that are considered. Each one needs to have its own bucket, right? So we basically say out of the 9 choose 4 ways of choosing 4 coins out of 9, we have 3 buckets. How many things go into the first bucket? The first bucket is this one. How many things go into the second bucket? And then how many things go into the third bucket? Okay, so how you break it up into these buckets kind of depend on what the problem is. But to figure out how many things go into each bucket is a counting problem. So that is resembling the calculation of the number of tickets that are that will give you a partial win in a lotto, because you have some winning numbers and some non-winning numbers, and we're trying to compute the number of tickets that has this specific number of winning numbers and this specific number of non-winning numbers. So that is how we map this problem into the lotto problem. So once we figure out the 21, the 70, and the 35, then we ask, okay, for each way, okay, so I'm looking at exactly 4 coins, 2 out of A, 2 out of B, then how many ways can we end up with 2 heads and 2 tails? Okay, that's the next thing we need to look into is, okay, so we can have both of the A's contributing tails, we can have both of the B's contributing heads, and so on. And then for each one, we also figure out the binomial distribution thing, to basically say the chances of having both of the A's landing on the tail and both of the heads landing on the head is this. Okay, the chances of 2 A's contributing the heads, both B's contributing the tails is going to be this. The chances of each type contributing only 1 tail and 1 head is going to be like this. So now we look at these chances and we add them up, okay, and then multiply that sum by the number of ways we can arrange. We can choose 2A, 2B's out of the 9 coins. Okay, so that was a long discussion, wasn't it? And one other thing that's really important is to understand when we are adding and when we are multiplying. So for that, next time I'm going to hand draw a picture because I didn't do that today. For that, you want to look at the whole thing in terms of a tree. Okay, so if you're tracking down things on a particular branch of a tree, that's multiplication. On the other hand, if you say, oh, this leaf node, this leaf node, and this leaf node, those are the things that I want, okay, then it's an addition. Are we doing okay so far? Okay, let's look at Nathan's picture. Okay, Nathan posted a picture. Not exactly the problem that we are solving, I don't think. But basically, every time you move from a parent node to a child node, that's multiplication. But every time you say, oh, this leaf node, this leaf node, this leaf node, this leaf node, they are all things that I am interested in, then you're looking at addition. So across, this term for that thing, across non-ancestor nodes, it is addition. Along an ancestry chain is multiplication. I think that's the that's the best way I can describe it. Is that okay? Let me see if I can. I'll do this. Give me a second here. Um, all right. So what I'm doing is I am looking at the picture that Nathan posted. So if you are moving down like this, from one node to a child node, so every time you traverse a link, is a multiplication. But every time you want to say, oh, this node, and this node are all the things that we are interested in, then you are adding. Okay, is that okay, or does it make it even more confusing? Because apparently I have a knack at making things more confusing than they are already. Yeah, it's a good diagram, but it doesn't, it's not mapping to the problem that we have. Oh, it is? Oh, okay. I did not realize that. 7. Hmm. All right. All right, so next Monday, I'm going to generate a graph. Basically not a graph, but it's going to be a tree, just so that I can show you, what I mean when I say, okay, here's a tree that is representing the experiments. It's not going to be an easy tree to draw because it's going to have a lot of entries, but I can write a program to generate that tree. More likely than not, the tree is going to look like something like this. I'm going to use nested lists, to kind of illustrate, what branch has which sub children in it. But it's going to be, complete, so that this way you guys can actually see, how the whole thing is generated. All right, so Chandra has a question. You have two combinations for each option, but they are both adding to 6 each time. So isn't it the same as 4 choose 2, or is there a reason to break it down? Um, I'm not sure what you are referring to, adding to 6 each time. Okay, 2A to B. All right. So this is 2A to B. There are 2 out of 2 ways. You choose 2 out of 2 of the A's. You choose 2 out of the 7 of the B's, and that's why we have the 21. Um, no, in the subgroups. Um, I'm not sure which part of the subgroup you're referring to. All right, so let me read that question again. You have 2 combinations for each option. 2 combinations for each option. Are you referring to the A's and the B's, being 2 combinations? Okay, so the 2 AT to BH. Okay. All right, so focusing on this one, the probability of this happening is the product of these two terms, because one is telling us what are the chances that both of the heads, both of the type A coins landing on the tail, and then the other one tells us the probability of both of the type B's landing on the heads. So I'm not sure where the 6 is coming from. I'm not sure what the adding to 6 is coming from. All right, so I have two choose 0 and 2 choose 2, but isn't that the same as 4 2 choose 2? You mean adding between this one and this one? But you cannot add the coefficients because the powers um, to each one of these probability is different. Oh, okay. Yeah, there's no way to combine these three, because um, they do not share the same exponent when it comes down to the probability of the heads versus the tails, because we have 0, 2 in this case, 2, 0 in this case, and then the 1, 1 over here. And then we have 2, 0, 0, 2, and then 1, 1 over here. So there's no way that I can see to simplify this any further. There's nothing you can factor out that can make the summation of these three terms any simpler. So not quite sure what Chandra is referring to. All right, so Dalton said, I think I get what you're saying, but you have to separate them since they are different types of coins. So the type of coins, is separated so that we have one side here, and then we have one side over here. And these two are multiplied, so we never really get into a situation where the 2 choose 0 and the 2 choose 2 can be added because they are because because this is one gigantic multiplication. So there's no the two coefficients, 2 choose 0 versus the 2 choose 2, they're not added. There's no way we can add these two. And then there's also no way to add the 2 choose 0 and the 2 choose 2 over here because they are multiplied by a different value. They are coefficients of a different value. You could replace two of them with 4 choose 2. Alright, so 4 choose 2 is 4 times 3 divided by 2, which is a 6. So I'm not really sure where we can replace with a 6 because 2 choose 0 is a 1, 2 choose 1 is a 2, so we only so all of these coefficients are either 1 or 2. So I'm not really sure where the 6 is going to be coming from. There's nothing here that can add up to 6. Yeah, because 4 choose 2 is 4 times 3 divided by 2 factorial. 4 times 3 is 12, and 2 factorial is 2, so 12 divided by 2 is 6. And I really do not see anywhere over here that has a 6 in it. Now we have the 0.6, but that's just the probability of landing on the head that I just randomly assigned to the type A coins. Yeah. If all the coins were the same, then you could use 4 choose 2. If all of them are the same, yeah, that would be a different story if they're all the same. So if they are all the same, then we end up with this scenario because they would all be in the same category. So if they're all in the same category, in that case, then we have the 4 choose 2, yes. So if they're all the same, then we end up with nothing in this case. We only have one type in that case. So so all four are coming from the same type, and we want 2 heads and 2 tails. So that's why we have 4 choose 2 as the heads, and then the other part would be the tails. Okay. Exactly. So because they are different, so now we have to break them up because one part deals with the type A coins and then the other part deals with the type B coins. And that's because the probability of landing on the head are different between those two different types. Now, having said that, it is important to understand why even in the case that we have no type A coins, I still insist to have exactly the same format because this makes this case 0A 4B not a special case anymore. So when you look at this from the perspective of actually writing a program to compute the answer, this makes the this is a more generalized approach, which means you just go through a loop. The loop is going to say, okay, it will iterate all the possibilities of how many A's can be in the 4 coins. So we have 0A, 1A, 2A's, because that's the total. We only got 2 type A coins. So with each iteration of that loop, then I look into the possibility of, okay, so with that, how many ways can I end up with 2 heads and 2 tails? And there's also another nested loop that can compute that. So that's basically the code that I use to generate the answer. Now this is handwritten, but the actual computed answer that I quoted down here is coming from a program. I didn't do this by hand. So there we go. All right, so we ended up not having enough time to actually talk about how to trace the Dijkstra's algorithm. So I'm going to defer the due date of that a little bit, which is going to be a little bit problematic because this means we are going to push everything down by a little bit. But it is posted. Okay, so I have now released the actual question because I did not change it from last semester. And the spreadsheet that it links to already has the solution to the problem. So it's not really that meaningful, but now it has changed. So there's no need. So I'm going to change the due date. Okay, it's not going to be May 4th, which is next Wednesday. So I'm going to change it to the Monday after that, which is it's not good from the perspective of we'll end up with a lot of things due on the same day, but I cannot help it because I didn't have time today to talk about how to trace it. So you guys can start to look into this, but I will talk about how to trace Dijkstra's algorithm on next Mondays. So I'm going to give you guys maybe I'll just give you 2 days to work on this next week, because I think it's not going to be that long. Once you understand the algorithm, tracing it is not going to be that much. So at any rate, it is not technically assigned yet. I cannot unhide it. Okay, that Canvas won't let me do it. But this is the actual problem that you solve. So I would say don't trace it to the point where that's going to be something that you want to turn in. But think about it, okay? Think about if you have a graph as described by this question here, looking at Dijkstra's algorithm, how are you going to solve the problem? How are you going to follow the algorithm to come up with the answer? But don't work on the spreadsheet just yet, okay? Because there's a particular format, and I want to talk about it before you guys get started with it. Whew, okay. Oh, May 4th should be a holiday. Yep. I would say so. I don't have a Star Wars t-shirt today, but most of the time I do. All right, so we are running out of time today. That's all we have time to talk about. So we'll talk about Dijkstra's algorithm, how to trace it on Monday, and then we'll get into the A-star algorithm as well on Monday. And then we'll see how much time we have left to talk about time complexity, which is a very useful topic. I think I'm going to prioritize time complexity over predicate calculus because predicate calculus is fun, it's interesting, but I would say in the grand scheme of things, it is not as important as time complexity. So that's kind of the general plan at this point. I used to, I'm not sure where I put it. I used to have a lightsaber that has a motion sensor. So when you whack it on something, it will give you that sound. I'll try to see if I can find it. All right. Just curious if anyone got this correct before class. Well, everything has partial credit, and I think on last year, which is this is from spring 2021. Most people get partial credit, for being able to identify certain aspects of the solution. It is a little bit long, I realize it is a little bit on the long side. Ah, okay. Yeah, so it's mostly the approach that matters. I'm looking at the solution of people to see if they were able to analyze the problem and separate all the different parts of it. So it's more of a application part. I mean, the actual numbers obviously is kind of tedious to compute. Yep. All right, so I'm gonna stop the live stream because it looks like I don't have anything else to present using the live stream, so I'm gonna get out of that. But I'll read the text channel until it quiets down. How about that?